Good afternoon, everyone. I, Dr. Shilpa Patel from Department of Chemistry, MCM DEV College, Kangra. So today I'll be presenting my oral presentation on the topic, that is my research work, metal organic framework based heterojunction photocatalyst for water purification. So particularly, we know that with increasing water pollution, there is a you can say emerging requirement, or this topic, the water pollution, it has become emerging topic of research due to, as the day by day, you could say, along with the other pollution, air pollution, noise pollution, water pollution is being the wastewater, you could say the water quality is being depleted day by day, right? So for that we need, as a researcher, we need to reform, or we need to find out, discover some method that needs to be efficient along with sustainable. The main thing is the sustainable. So particularly I have worked on this, so the introduction part. So I have particularly targeted some of the pollutants, that is the antibiotic and the dyes, right? And in that also I have used antibiotic, that is sulfamethoxazole or nidazole and rhodamine B. I have always taken a targeted pollutant so this is the targeted pollutant. The scope for research will be like, you can even do the study with the other targeted pollutants, pesticides, or other categories of the antibiotic, right? So why I have chosen this sulfamethoxazole particularly, or nidazole, because of their non-biodegradability, right? Prolonged half-life period, they stay for 85 to 100 days in a wastewater, you could say, right? So that's why I have taken this in my study. Next is the way we need, as I'm talking about the sustainable treatment technique or purification technique. So till now, whatever the conventional techniques that is being used, that is the biological degradation, coagulation, flocculation, membrane filtration, adsorption, sedimentation. These were the conventional techniques that is being used. But this conventional techniques have a number of drawbacks, like high production of sewage sludge. They are cost ineffective, time consuming, and you could say the photocatalytic degradation efficiency, we could say, that is, they constitute a very less amount, right? So we just move towards the advanced oxidation processes. These oxidation processes takes place in the presence of solar light energy, right? So I have particularly taken the photocatalysis advanced oxidation process, photocatalysis based advanced oxidation processes. Why I have opted this? Because there is the solar light driven processes, right? And the production, basically we acquired the high number of reactive radicals with rapid degradation, fast degradation, with very minimal consumption of chemicals, right? Next, in this presentation, I'll be discussing the brief concept along with the material designing and the key result in my study that I'll be discussing. I'll be compiling like this. So you could say the photocatalytic mechanism. This is the basic mechanism. If I take any semiconductor, let us suppose titanium dioxide, I'll be showing in the next slide also. See, this is the titanium dioxide and zinc oxide, which is considered as a UV active photocatalyst, right? So, what is the catalytic mechanism? As in the presence of light source, what is happening? Photoexcitation of electrons that is taking place from the valence band. We know that semiconductor that is composed of a conduction band and a valence band. So photoexcitation of electrons that takes place from a valence band to the conduction band and leaving behind the holes. These electrons and holes are being further used to form the reactive radicals, that is the superoxide radical and the hydroxyl radical, that is the reactive oxygen species, that is we are using for the photocatalytic degradation in wastewater treatment, right? So, but what we have observed that with the bare photocatalyst, there's some limitations, because you could say there's an electron hole pair recombination is taking place, that is a very fast. So that's why what we can do, we can just do two photocatalysts we can take and we can combine it, right? And these are the drawbacks. Obviously the rate of recombination among the electron hole pair is very fast, and obviously the most of the photocatalysts, they are the UV active, so the solar light absorption will be less. If I talk about the photocatalyst that will absorb the light in the UV region, so there's only 4% of solar light energy will be observed. In the case of, if the photocatalyst in the visible absorptivity comes in the visible region, that photocatalyst will absorb maximum 40 to 60% of the solar light. So we need to fabricate, we need to combine the two photocatalysts in order to have the maximum solar light visible absorptivity, like maximum light harvesting capability, right? So that's why this can be done. So this was my research work also, that the heterojunction, I focused more on the heterojunction construction when we combine two photocatalysts. But ऐसा नहीं है कि दोनों photocatalysts को ऐसे ही mix करके physical mixing करके combine कर दिया. We call that as a composite. कोई भी दो चीजें mix कर रहे हैं, अगर एक interfacial contact बन रहा है, अगर वो adhere हो रहा है एक photocatalyst पे दूसरा, तो we call it as a composite. But I am here talking about the heterojunction construction. What is the difference if I talk about एक composite और heterojunction में क्या difference होगा? तो difference ये होगा, अगर हम दो फोटोकैटलिस्ट को मिक्स कर रहे हैं, दैट इज फॉर्म एज ए कंपोजिट. अगर उसकी कोई अगर हम उसमें देख रहे हैं फोटोकैटलिस्ट, आई ओके डिस्कस दिस लेटर ऑन. बिफोर दैट आई हैव पर्टिकुलर टारगेट दैट मेटल ऑर्गेनिक फ्रेमवर्क. दिस आई ऑब्जर्व that in maximum of the traditional semiconductor, for example Ti2 and ZNO I have given because this is a UV active photocatalyst, their band gap is around 3.2 electron volt. So I moved towards the MOF for the heterojunction construction, which I observed that in the MOF also I have taken the MIL series MOF. MIL means material of institute Lavoisier. In that also particular 88A, MIL 88, that is a one kind of MOF. That is like you could say that also I have taken in respective of taking it as a you can say the green taking this thing in mind that it will be a non-toxic. So MIL88A, that is composed of a fumaric acid along with the ferrichloride hexahydride, that was the precursor, and they are non-toxic in comparison to other series of iron-based MOF. So that is why I particularly take this. Right? First, in what happened, you could say these MOF, these are the example of some of the MIL series MOF. You could say that their band gap is less than 3.1 electron volt. That means it will be going to observe maximum of the visible light region, right? Also one thing I have discussed about metal organic framework based photocatalyst. So what is MOF? MOF is nothing but it is a crystalline compound which is composed of a metal ion or metal cluster which is connected with the organic linker. So in my work, what I have used the metal ion, that was iron, and the organic linker was the fumaric acid, which is non-toxic in nature, right? This was the composite. What I have done, I have taken this MOF and I have just combined it with two other MOFs, right? If I talk about the strontium titanate, it is manganese dot strontium titanate along with the cobalt oxide and the MOF. Now, this was a once summarized picture. You could see the graphical abstract. You can see this was the heterojunction construction, not the composite. Why? Because it is defined on the basis of electron hole pair charge pathway, right? So how the electrons is being combined with the holes. So this also I discussed this mechanism in detail in this picture. This was the main mechanism which I drawed in my, which was I have find when I have synthesized this bare molecule and combined it as a composite. So heterojunction, there's a different types of heterojunction construction is there. That is also quite long topic. So the traditional heterojunction, if I talk about, that is the type 2 heterojunction. In type 2 heterojunction, there is nothing but there's a combination in such a way that whatever the balance band, the lower balance band of one semiconductor, they will just follow the whole separation to the other photo catalyst of having a balance band of there will be a difference in this way, right? On the other side, the electrons will be transferred to the conduction band of other semiconductor, right? So electron will always transfer like this, and holes will excite to other valence band, right? So this was the traditional type of heterojunction construction, and what I have found out in my research work that it was found to be a S-scheme. This is the advanced version of heterojunction construction. What is the eligibility or what is the criteria to form this S-scheme? S-scheme dual, I have mentioned here the word because you could see the simultaneously two electron recombination that is taking place, right? So also one more thing you can see, I have taken this MOF. These all three of the photocatalysts, they are having the band gap around 2 electron volt. So there's a narrow band gap. So definitely the target to achieving the maximum solar light absorptivity was achieved here only. And if I combine the 3 different photocatalysts, obviously the result showed the absorption of visible light region is up to 540 nanometer. That I'll show you in results. So this was the synthesis process. Synthesis process was simple. It was the hydrothermal method I have used even for the bare photocatalyst also, and for the binary or ternary composite I have opted the hydrothermal because it acquired the highest purity along with the you could say the lower amount of you can say we need the less amount of precursors, and the yielding rate is quite high. Also, this is, you could say, if I want to maintain, as per the literature, my MOF which I have synthesized in a specific reaction condition, it was of hexagonal rod-like morphology. So I need to maintain this morphology, so that's why I opted this hydrothermal method. Okay? Next is the validation. This is the characterization through which the material designing that is being, you could say, validated. I'll just talk about the MOF only. You could say the crystal plane. This could be appeared when I talk about the heterojunction ternary composite. It could be appeared that it shows the purity of sample also, and the presence of this ternary heterojunction formation is all there. If I talk about the FDIR spectra, here you can say.
Hello. If you could please hurriedly conclude.
Yes, sure. So next, okay, I'll discuss, as I discussed, the rod-like structure morphology is formed in the case of MOF. You could see this SEM image. In this, the confirmation, the image shows the rod-like morphology, right? So this next is the defriezing. This is the EM images. These also, anyhow, this confirms, this validates the formation of this composite, and further the heterojunction construction. And I just discussed the XPS analysis, why I presented it, because this is required in the heterojunction construction. If it is asked how are you going to confirm that heterojunction construction or your composite is formed through the XPS. So this is the this is the primary characterization we require, and see all the peaks they could be, you could find out. So it shows the purity of sample also if it is a bare or composite. Next is the optoelectronic properties. So I'll just show this. The conduction band and valence band, it was fine. I have found it through the Mott-Schottky curves, from which I found the accurate conduction band and valence band, and with this I formed the heterojunction construction that was dual S scheme. This is the application part. So I'll just conclude with the application part that maximum 95.5% sulfur methoxazole degradation was done in 60 minutes, and maximum visible light region absorptivity up to 540 nanometer was achieved. This is my research profile till date, and thank you so much.
Thank you for such an illustrative presentation. Any questions? Okay, thank you, ma'am. With this, we conclude today's